Hello everyone, you are welcome to another series of Python for chemical engineers. This is Meshed Up Mentors. In today's video, we will dive straight into application of Python in solving equation of state problems. We'll import our respective packages, which is NumPy, Matplotlib, and from scipy.optimize import fsolve and roots. Having imported our respective packages into the namespace, the next thing we do is to look at the background on a few equation of states. The first is the Redlich-Kwong equation of states, which is RK. The Redlich-Kwong equation of states is a modification of the van der Waals equation. And so we have it as defined here, where A is defined as you can see on your screen, likewise B, and same alpha. The next is the Redlich-Kwong swerve equation of states. It has same definition, but a slight modification from RK equation of states, where we now have M in the form of the eccentric factor introduced into alpha. Okay, so we have these various expressions, okay, defining the RKS equation of state with A, B, TR, alpha, and M. Third is the Peng-Robinson equation of states, where we have the general expression as described as you can see on your screen. Okay, and then here we have A, B, and alpha with inclusive of M, which is defined in terms of the eccentric factor. Let's do a simplification here, and what we're simply doing is to rearrange this expression here, okay, and write it in, in a very simple term. And so if you rearrange that expression, we can factor out the specific volume, which is a V bar, and we have it as V cubed into P, V squared RT plus V into A minus PB squared minus RTB, then minus AB equals 0. For each of these equations of states, we'll be obtaining the specific volume so that with the specific volumes, we can, determine the compressibility factor. And so to do that, we solve the left-hand side. For pure component, the parameters A and B are determined from the critical temperature and critical pressure, and possibly the eccentric factor. But for mixtures, it is necessary to combine the values of A and B for each component according to the composition of the gas. And so if you are dealing with mixture, all you simply need to do is to further define, obtain your A by using the mixing rule. And then you can apply the corresponding equations of states to find the specific volume. Let's go straight to problem one. Problem 1 says find the specific volume of N-butane at 500 Kelvin and 18 atmosphere using the Redlich-Kwong equation of state. The source of this problem is from Introduction to Chemical Engineering Computing, Bruce A. Freelason. So we go straight to the solution, and in the solution, I define volume underscore RK takes volume, temperature, pressure, critical pressure, omega, which is the eccentric factor, and the gas constant R. Now we know these values, so we can pass in default values. Likewise, if it changes while you're solving, you're also free to pass the new value. So for RK, what we have, we'll go back to the equation. This is RK, so we have our TR, which is the ratio of T over TC. And alpha is 1 over the square root of TR, which I've expressed here. Likewise, A and B. And it returns the expression which we have simplified, shown here on your screen. Let's define our parameters TC and PC for N-butane, which you can obtain from literature or you're obtaining from textbook. And then we have T equals 500 and P equals 18. Remember, pressure is in atmosphere, and that's why our gas constant is in 0.08206. So first, we'll call V1 equals, I'm using the roots function to solve this problem. Pass the callable function in, make an initial guess of 2, and then pass my args. My TP, TC, and PC are all args. And here I'm printing the results. And what we have, the specific volume of N-butane gas is 2.2037. Using FSOLVE to solve the same problem, call FSOLVE past the function callable, initial guess, and the args, the same way we are passed for roots. And then we run again. What do we have? We have the same result. The specific volume of N-butane using FSOLVE is this. So you can either use FSOLVE or use root. But notice the way the result is being assessed. In root, result is assessed by calling V1 or whatever variable you have used, name you have used, dot x of 0. That takes the first item. But in FSOLVE, we assess the array directly. With that, we move to the next problem. I want to repeat the same problem here, solving it with RKS equation of states. And so I will define all my variables TR, M, alpha, A, and B as we have listed in this equation for RKS. You can see that here, what I've defined in the function and all of this, and it returns this simplified expression. Okay, and that's what we have here. So also likewise define the parameters which we have already defined earlier. So we have it in namespace. So I run this cell and then use the roots to solve. Here I also make a guess of 2 and then pass my args and then print the specific volume. What do we have? It returns 2.0583. It's quite close to the results of RK. Next, repeat the same problem with Peng-Robinson equation of state. All of this expression we have here is defined up. Let me take it up so you see where I've defined for Peng-Robinson. This is for Peng-Robinson. In the same vein, it returns this simplified expression. And so I can come down here and return again the same expression. If we run this cell and then we have the function and namespace, we compute for V2, I think let's call that V3. And so I can access V3. Here I'm using again roots to solve, and notice the way I'm assessing the result. It is V3 dot x of 0. If we run this cell, returns the specific volume is this. What if I decide to use fsolve? If we use fsolve, what you simply have is that you have to assess the result by v of 0. If we run, what we have specific volume is this. So you can use any of the solvers and you'll get the same result. Let's go straight to problem 2. Here we want to compute the compressibility factor using the result from our previous example or previous problem. And so I want to do that for RK, RKS, and PR so that I can plot the result and compare the result and see how the results vary. So what we do here is pick a range of pressure. We already been picking pressure to be 18, so I just extend the range of pressure from 1 to 30 with interval of 2, and then create an empty list for the compressibility factor for RK, RKS, and PR. Then what I will do to enumerate now was to loop through the range of pressure. And notice what I'm doing here. I'll first of all calculate an initial guess for the specific volume, which is RT over P for each of the pressures. So once I calculate that, I will pass that in for the first volume, which is computing the volume of RK, calling the function V underscore RK and passing the args, the same function the signature. And the result of that will be used to compute Z. Once the Z is computed, it is appended to the list ZRK. But when I move to compute compressibility factor for RKS, I'll no longer use the initial guess, rather I'll use the volume computed for RK as the initial guess for RKS. And likewise, I'll do the same for computing the specific volume for Peng-Robinson equation of state. And then lastly, here I'm trying to visualize the results. So if we run this cell, we can see a plot of how the compressibility factor vary with pressure for Redlich-Kwong, Suave, and Peng-Robinson equation of states. Let me correct this. Run again, it gives us this plot. Now we go straight to the next application, which is in chemical equilibrium, and then we'll look at chemical reaction equilibrium before we end this video. So here I just take a simple expression. We know this expression here, which is a right for rise equation. Okay, V prime is the mole ratio of the molar flow of the vapor to the liquid. So we know our corresponding Z, we know our values of our K. All I need to define a function which is known as VLE, and it simply returns the value V, which is the molar flow ratio. First, I'll define a result equals zero. To be able to code this expression, I have to first of all assign a zero value to result and then loop through for each of the species, which is for each of the items, I'll loop through and then accumulate the results because of this summation. So in looping, I use a very efficient way of looping, which is zip. So I have Z and K in zip, Z and K, and then accumulate the results and then return the results. Let's see what happens if V is zero point 0.2. We print the result as zero point 0.2. This is the result. Now, to obtain the value of the molar flow rate, I use fsolve and I make a guess. Here I'm guessing zero point 0.2 and then I'm printing the result. And what do we have? It returns 0.425. What if we try to resolve this same problem by rewriting this function in a different way? How do I have done that? I simply have created a list comprehension, perform my loop in a list, and then passed it to a sum function. So instead of using, first of all, defining result equals zero and then accumulating it, I just do it as a one-liner, sum the list comprehension. And so if we run this to have it in an namespace, we can solve, fsolve, and then it returns the same result. Likewise, we can compute the liquid and the vapor composition using this expression here. So to do that, I've called x equals np array. I have a list compression right in there. Likewise, I do that for what? For y. And then let's print the result. If you print the result, what does it return? You see, it returns an array for us. If we want to put this or re-represent this here, we can come here and modify how we print return the result. We can either use a flatten, because the numpy array, you can either flatten the array or use the Ravel function. If you flatten that and you run again, you see it returns a single list for the mole fraction, mole liquid fraction, and the vapor liquid fraction. Okay, the last problem here, but not the least, is the chemical reaction equilibria. The reason why I'm taking representative problems here is that once I've solved a simple problem, it's easier for you to apply that to solve a variety of problems, even more complex problems that I've addressed in this video, knowing the fundamentals. So here we have the water shift gas reaction, CO plus water equals CO2 and H2. And then the reaction takes place in a fuel cell at equilibrium. Given the equilibrium constant at 500 Kelvin, compute the equilibrium mole fraction. Okay, and so this is the expression to solve this. The equilibrium constant is equal to the mole fraction of YCO, Y hydrogen, and the mole fraction of CO, and divided by multiplied by mole fraction of water. Here, the equilibrium constant is the mole fraction of CO2 hydrogen divided by the mole fraction of CO and water. So I define a function VLE underscore reaction. It takes X is my parameter, which is the equilibrium mole fraction, okay, followed by additional parameters or argument that I want to pass in, with K equilibrium equals 148.4. So now I want to unpack my parameters. So the mole fraction in for CO, water, CO2, and hydrogen, I unpack them as my parameters. So that I can define the final moles of CO, hydrogen, and water. Likewise, CO2 to be CO in minus X, the equilibrium mole fraction. For water, it is minus. But for CO2 and hydrogen, it equals the in plus the equilibrium mole fraction. And then it returns the K equilibrium minus this expression. All I've done here is to transfer the right-hand side to the left-hand side. You can equally transfer left hand side to the right hand side, and then you solve, you get the same answer. Using F-solve to solve, all we need to do, what are my parameters? The mole fraction in is 1, 1 for CO2 and water, initially is 0. And so initial guess, I make a guess of 0.5, apply F-solve, and then print my result to two significant figures. What do I have? The equilibrium mole fraction is 0.92. Using the root function to solve, same call root, pass the function in, initial guess, and the args, print the result. What do we have? We have equilibrium mole fraction is equal to 0.92. We have come to the end of this video. Like this video and share this video with your friends, relatives, colleagues. And also, if you are watching this video for the first time and you are coming across my channel for the first time, please subscribe to my YouTube channel and turn on the notification button so that when I release future videos, you will get notified. I will see you in my next video. Bye.